Hello students, welcome to this small session on numerical solutions to ordinary differential equations. So in these modules of numerical analysis, we have seen numerical methods for different purposes in mathematics, right? We have seen numerical differentiation, and we have also seen how integrations can be done numerically. And later we discussed curve fitting and interpolation kind of things, right? So now it is the turn of differential equations. Here we will discuss numerical solutions to differential equations, starting with a very simple problem, that numerical solutions to ordinary differential equations. Okay, so there are basically two methods to discuss here. So first method is Euler's method, which will be discussed in this session, and there is also another session, another method which is a second order method, which is called Runge-Kutta method, or RK to RK method. Okay, it's Runge-Kutta, written like this, which will be discussed in the next class. Okay, so you are already experts in solving differential equations because you have seen different kinds of differential equations that represent different physical systems, different systems in physics. And you know how to solve many of such equations analytically. Okay, so now as we have seen in previous lectures, analytical solutions to mathematical problems are not always possible, right? So same is the case of differential equations. Many of the physical systems represented by differential equations are not analytically solvable. Okay, so many physical systems, many physical systems that are represented by differential equations are not analytically solvable, not solvable analytically. Okay, so in such cases, we know that we have to resort to numerical methods, right? So which is the entire idea of these modules that we are discussing now. Okay, so we will start with a very simple problem, like solving ordinary differential equation using numerical method, and the method we are going to discuss is Euler's method. Okay, so like in the previous discussions, we know that when you go for an analytical solution, you get an exact solution. Okay, but numerical solutions are always approximate solutions. Okay, and once we get the solutions, we have to make sure that our solution is genuine one. I mean, we have to make sure that error in our solution, numerical solution, is veritas. Okay, so these things will be discussed later. Okay, so basically we are going to discuss approximate solutions to first order ordinary differential equations. Okay, so we'll start with start by writing a general form of first order ordinary differential equation, which looks like this. We already know this. Okay, so df by dx equal to f of xy. So this is the general form of a first order ordinary differential equation. Okay, so for example, uh, if we take an equation like y dash minus 2y equal to 0, so this is a first order differential equation. This here y dash is dy by dx, right? So this is like dy by dx minus 2y equal to 0. So that's the equation, right? So if you want to write this in general form, this will look like y dash, or let's say dy by dx equal to 2y. Okay, so now this equation is written in general form. Okay, so now usually if we want to solve a differential equation using Euler's method or any numerical method, we need to know an initial condition. We need to know an initial condition. Okay, initial condition mean the solution to the problem at least at one point. Okay, and we take it as the initial point. Okay, so we should know basically x0, y0. Okay, at a point x0 we should know what is the value of y0. So this should be given. Okay, so once this is given, we can solve an ordinary differential equation written in this form using Euler's method. Okay, so such kind of problems are called the initial value problem. Okay, there is a first order differential equation and the initial value is given. I think I have written the definition here. Yeah, so let's take this. So these kind of problems are called initial value problems. Okay, an ordinary differential equation together with an initial condition. Okay, so all right, so now let's look into how Euler's method enables us to solve an ordinary differential equation. Okay, we'll not look into the detailed theory, but the following discussion will give you an idea of how an ordinary differential equation can be solved using Euler's method. Okay, all right, so before we go to that, let's see what will be one of the initial condition for this uh, equation. Okay, so for this equation, we know the solution of this equation, right? So solution of this equation will look like y equal to exponential minus 2x. Okay, so if we have this solution, then dy by dx is minus 2 exponential minus 2x. Okay, so now if you substitute here, so dy by dx is this, so this will give you minus 2 exponential minus 2x equal to 2 into uh, 2 into just hold on, I think this is exponential e power 2x. Okay, so there will be no minus here, so this will be plus, so this will be plus, so this is equal to, so this is dy by dx. Okay, so that is equal to 2y, so 2 into y is this the solution, right? Exponential 2x. Okay, so that is satisfied, so this is a solution. Okay, so how will an initial condition look like? So initial condition x0 y0, for example, if you take the value of x0 is 0, then what is y0? If you put x here, 0 here, exponential 0 is 1. Okay, so x0 y0 equal to 0 1 is an initial condition. Okay, so an initial value problem basically will be this equation. Okay, so we'll write it here, y dash minus 2y equal to 0. So if you look for an example, y dash minus 2y equals 0 along with an initial condition x0 y0 equal to 0 1. Okay, so now this is an initial value problem. Okay, and that can be solved using Euler's method. Okay, so now let's look into how Euler's method can give us a solution. Okay, so we will remove this now, so we'll remove. Okay, so as I told you, we are not going to the complete theory, but this discussion will give us an idea of how the method works. Okay, so we start with the differential equation. We have an equation dy by dx equal to f of xy. Okay, and the initial condition is given like y of x0 equal to y0. Okay, or x0 y0. Okay, so this is given. Okay, so this is initial condition. initial value. Okay. All right. So now let's assume that this is the solution. Okay, so if you solve this equation, it will give you the y values for all the x values. Okay, so once you have y values for all the x values, we can basically plot it. Okay, so let's say the solution is this. Okay, we have plotted the solution and it looks like this, for example. Okay, and what is the initial value? Initial value is the value the beginning. Okay, so this is x0 y0. So this is x0 y0, 60. Okay, and the corresponding solution y0. Okay, and this is the exact solution, or let's say this is the analytical solution. Okay, so this is the solution. Okay, this is the exact solution. Let's say this is the analytical. Okay, so now what we need to find out numerically is we know only this point. Okay, we know only the initial value and we know the differential equation. Okay, and we need to find out what is this numerically. Okay, so we don't know this solution, we don't know the red curve. Okay, and we are going to find out approximate solutions using Euler's method. Okay, so now we proceed like this. So we know, okay, so we have dy by dx. Okay, so we have dy by dx is f of xy. Okay, and we also have the initial condition x0 y0. Okay, so this will give us, since if we substitute this here, it will give us dy by dx at the initial point. Okay, at x0 y0, and that can be obtained by substituting x0 y0 here. So f of x0 y0. Okay, so once we know this, we can actually draw, we actually get the slope here. Okay, so with that we can draw a tangent at this point. Okay, so let me draw a tangent here. Okay, we'll take a line. Okay, so let's see how it works. Okay, so this tangent, okay, so let's assume this is the tangent. Okay, so this tangent will give us the slope here. Okay, so now from this, basically, we can actually find out what is the solution at a neighboring point. Okay, so now if we take a point x1, okay, the corresponding y1, corresponding solution y1 can be obtained from this slope. Okay, so that can be done using, if we write the equation for the slope like this, so dy by dx at x0 y0, we already know this, so this is written as y minus y0 divided by x minus x0. Okay, so now if we take a neighboring point, okay, so before that let's write this in a different form. So from this we can write y minus y0 equal to, take this to the other side, x minus x0 into dy by dx at x0 y0. Okay, and from this we can write a value for y, keep y here and take everything to the other side, so y equal to y0 plus uh, x minus x0 dy by dx at x0, oops, x0 y0, right, y0. Okay, so now if we take a neighboring point y1, sorry, x1, let's say here, if we take an x1, then we can get from this slope we can basically get the corresponding y1. Okay, we can get y1, and you can see that this y1 is almost equal. You see, it's very close to the actual solution. It's not, it's an approximate solution, it's not an actual solution, but it is very close to the approximate solution. So the approximate solution comes here, and sorry, the actual solution comes here, and this is the approximate solution. Okay, so and the closer the point, the closer x1 to x0 is, the better is our solution. Better is our approximate solution. Okay, so we can, from this equation, we can basically write an expression for y1. So y1 equal to y0, you put x1 here, right? y0 plus x1 minus x0 dy by dx at x0 y0. Okay, so this dy by dx is basically f of x0 y0. Okay, so we can write this as y1 equal to y0 plus x1 minus x0 f of x0 y0. Okay, so now what we can do, so basically we have now x0 y0. Okay, was the initial condition, okay, or the initial value, and from this we have also found out x1 y1, solution to the differential equation at a neighboring point to the initial point. Okay, so this is approximate solution at a point very near to x0. Okay, so now we can get an approximate solution. From this we can get an approximate solution to at one more point. Okay, let's say x2. Okay, so from this we can get an approximate solution at x2. Okay, x2 is a point which is very close to x1. Okay, so how will that look like? So we can write an expression for that, looking at this, right? So that will look like y2 equal to y1 plus x2 minus x0, right, into f of x1 y1. Okay, so this will give us x2 y2. Okay, so now we have x0 y0, x1 y1, x2 y2. Okay, so basically we are getting solutions at neighboring points. We had solution here, we found a solution here at x1, and we found a solution at x2, and this can be continued, right? So this can be continued. So basically we have drawn a tangent here for the first time, and then we have drawn a tangent at next point, and we draw a tangent at here. So instead of the actual solution, we will be getting an approximate solution, and the curve will go like this. Okay, all right, so let's write the equations now. So this will be an equation for, this is the equation for y2, and the y3 can be obtained in the similar way, y2 plus x3 minus x0 f of x2 y2. Okay, so with this we'll have x3 y3. Okay, and this can be continued. So now we can write a general equation like y, if we have yn, we can write an expression for yn plus 1, like yn plus we'll write it like this, f of xn yn multiplied by x xn plus 1 minus xn. Okay, so now we can choose our own x1. We have basically choose our own x1 white, our own x1, x2, x3, like that. Okay, so what is the easy method to choose x1, x2, x3? We can take equal steps. Okay, so if you take equal steps for x1, x2, x3, etc., we can basically call xn plus 1 minus xn equal to h. Okay, so that this equation can be written as yn plus 1 equal to yn plus h f of xn yn. Okay, so this is the basic equation for solving an ordinary first order ordinary differential equation using Euler's method. Okay, so this is the general equation. Okay, or let's say a general solution. Okay, so now as usual we will go for solving an example. Okay, so let's start with a very simple one. I think I have written the solution, the equation somewhere here. Okay, so we'll take this. Okay, so we'll start with this example. So this is the differential equation given. Solve y dash equal to minus y with an initial condition y of 0 equal to 1. Okay, using Euler's method. And it is asked to take h equal to, we'll start with h equal to 0.2. Okay, take h equal to 0.2. If it is not given in the question, you can choose your own value for the step. Okay, so we'll start by writing the general Euler's general equation of Euler's method. Yn plus 1 equal to yn plus h f of xn yn. Okay, so y of 0 is given, it is 1, so we have x0 y0 equal to 0 1. Okay, so now we need to find out first value y of 0.2, okay, which is equal to, let's say y1. We'll write it like this. Okay, so this is y0. Okay, so we'll now see y1, which is y of x0, y of x1. Okay, y of x1, which is y of 0.2. Okay, because x1 is 0.2, h is 0.2, so x1 is 0.2, x2 is 0.4, right? x3 is 0.6. We'll go until x4. Okay, x4 is 0.8. Okay, so y of 0.2 equal to y0 plus h f of x0 y0. Okay, so y0 is okay, hold on. Yeah, so y0 is 1. Okay, plus h we took as 0.2 into f of x0 y0 is 0 1. Okay, so f of 0 1 is here. So this is our equation, y dash equal to minus y. Okay, or dy by dx equal to minus y. Okay, where this is the this is f of xy. Okay, when you write it in general form is dy by dx equal to f of xy. Okay, so f of xy is minus y. Okay, minus y. Okay, so this will be okay. So now this is going to be minus y. So y is 1 here, so this is minus 1. Okay, so this will be 1 plus 0.2 into minus 1, which is 0.8. Okay, so we got x1 y1. Okay, 0.2, 0.8. Okay, so we had x0 y0. Oops. Okay, we had x0 y0, and from that we found out x1 y1. Now we had for x2 y2. Okay, so y2, which is y of 0.4 equal to y0 plus h f of x1 y1. Okay, so sorry, this y1 here. Okay, so that's going to be y1 is 0.8, 0.8 plus 0.2 into f of x1 y1. So f of x1 y1 is minus y1. Okay, so this is minus y1, which is minus 0.8. Okay, so that's going to be multiplied by minus 0.8. Okay, so if you do the multiplication, this will be 0.64. Okay, so with that we got x2 y2 is 0.4, 0.64. Okay, so now we go for y 0.6 equal to y2 plus h f of x2 y2. Okay, so y2 is 0.64 plus 0.2 into minus 0.64. Okay, so if you do that, you will get 0.512. Okay, yeah, 0.512. Okay, so we have x3 y3 now, which is 0.6, 0.512. Okay, so in the same fashion you can also do 0.8. I will not do it here. So when you do that, you get x4 y4 equal to 0.8. 0 point, the value will be 0.4096. Okay, so we basically got all these values. Okay, so we basically got, we started with this, we got this, and this. Okay, so now we can draw the solution. Okay, so we'll do that. We'll go to MATLAB for that, and we write a code for Euler's method, and we'll plot it. Okay, so before that, let me just once again go through this, the problem example. So this is the solution, this is the differential equation, okay, with an initial condition given, and using Euler's method we have basically solved this. Okay, we have solved this means for different x values, x1, x2, x3, x4, we found out corresponding y values using this equation. Okay, so now we are going to plot the solution, and we will compare it to the uh, the analytical solution. Okay, so we know the analytical solution to this equation, right? So this is a very simple differential equation, y dash equal to minus y. Okay, and the analytical solution is uh, exponential minus x. Okay, so y equal to exponential minus x. So if you do that, dy by dx equal to minus exponential minus x. Okay, so that we have y dash equal to minus y. Okay, so the solution is satisfied. You have solved this several times before. Okay, so we have the analytical solution. We also got the numerical solution, and we are going to compare that to know whether our numerical solution is correct or not, or how good is our solution. Okay. Okay, we will take the help of ChatGPT to write a code for Euler's method. So we can ask like, write a MATLAB code for solving first order differential equation using Euler's method. Let's take h as step because we used h, and take x and y as variables. Okay, otherwise it may take x and t or t and y, whatever. Okay, so we need to we can have our own variable names. Okay, so let's see what it makes. Okay, so this is the code generated. We can now copy this. Okay, but we need to plot it. It does not have a plotting command. Okay, so I will ask include plotting as well. Okay, so now okay. All right. Okay, so we will now copy this one, right? Okay, copy code, paste it in MATLAB. So I opened the script. Let's first save it. Euler sample. Okay, it is saved now. Okay, now let's go through this. So the first line is define the function here. Okay, so we have to define the function here. So this is how function is defined. So let's say x plus y. So instead of this, we have to give our function probably, how do we do that? Let's try f of xy here. Okay, so here we have to give our f of xy is minus y, right? Minus y. Okay, so we give minus y here. Initial condition x0 is 0, y0 was 1, so we put 1 here. H, okay, we will have to put 0.2. Xn is the last value of h, so we will solve up to 2. Okay, in the problem we have solved only up to 0.8, but we will go up to 2 here. So n will be calculated like this. Okay, xn minus x0 by h, so there will be 20 values, 10 values, right? Okay, so okay, these are arrays, you know how it works. Okay, so everything is now done. Let's try to run this. Okay, we have now everything. Let's now plot the do the calculation and plot the result. We are taking h equal to 0.2. So let's run the code. It should plot. Okay, so it plotted the solution for h equal to 0.2. So now we are going to change the h value. We are going to reduce the h value to 0.1. Okay, and do the calculation again, run the calculation again. Okay, so this time we will plot it with a different color, red. We'll use circles. Okay, so let's plot. Okay, you see, so the green one is the previous solution and the red one is the new solution. The green one is with h equal to 0.2, so let's put legend so that we can differentiate them. H equal to 0.2 and the new one is for h equal to 0.1. Okay, okay, you see the legends are here and they are almost equal. Okay, so now let's compare this to analytical solution. So we can directly plot the analytical solution along with this. So we can plot x comma instead of y, we'll plot exponential, that's the solution, right? Exponential minus x. Okay, and we'll use a different color. Let's use black. Okay, will do. Okay, all right. So you see, so that's the, we'll maximize. So the black one is the analytical solution, which is the exact solution. Okay, and the green one and red one are our attempts to numerically calculate the solution using Euler's method. When we have h equal to 0.2, we have the green one which gives an error. Okay, and then when we reduce h, obviously we get a better solution. Now the red one for h equal to 0.1 is very close to the actual solution. Okay, so now what we can do is we can reduce the h further. Okay, let's go for h equal to 0.01. Okay, so we will do h equal to 0.01. So we should get exactly the same analytical solution. Okay, exactly the solution should be now very similar to the analytical solution. So we'll use a different color. Let's go for blue and we'll go for blue dots. Okay. Mm, okay, go for stars because they are easy to see. Okay, so we run the code again. You see, now we got the solution. We should zoom now to see them very clearly. We should zoom somewhere here. Okay, you see, so the black one is the analytical solution, and these blue dots are the Euler's method solution for value of h equal to 0.01. Okay, so we'll see, give now proper legends. Okay, h equal to 0.1 was the next one, and then we calculated uh, h, no, analytical. Okay, then we did the last one, h equal to 0.01. Okay, so that's it. So it is okay. So there's everything now. Okay, so that's it. Uh, okay, so we'll go back to the notes. Okay, so basically we have solved this differential equation using Euler's method. Okay, first we have solved it using pen and paper here, right? And then we made a code for the same, and the code is executed in MATLAB, and I have pasted the result here. And now what we can do is usually, as usual, you can split into 4 groups, okay, and find your own problems, okay, find the differential equation and solve it using Euler's method, okay, and make sure that all the 4 groups have different problems. Okay, and the fourth group will have 5 members, right? Okay. All right, so that's all. We'll see in the next.